Okay, so good morning. Здравствуйте. Hello, everybody. I'm very happy to be here. This is my, I don't know, 15th time in Russia, maybe. So it's very bad that I cannot speak much yet in Russian. Sorry about that. So I'll go in English. So my name is Álvaro, and I'm going to speak today about Postgres on Kubernetes, which I'm sure is an interesting, hopefully it's an interesting topic for you. The first thing I would like to say is that please stop me anytime. This is going to be a 3-hour session. It's, for me, it's extremely early in the morning. I'm a night owl, I'm a night person. So otherwise, it's going to be likely hard. So make it harder for me. Make it easier for you by asking questions. Interrupt anytime. If you're not totally fluent in English, try anyway. I'm definitely not fluent either, and I'm sure anyone could help. So please stop me anytime, okay? This session, it's very risky for me because I'm going to spend most of the time on the console typing commands, which means everything will fail. You will laugh at me, but hopefully between all of us together, we'll fix all the issues that will come up for sure, and we'll be able to have a little bit of fun. So the goal for me today is to show stuff that in a way that you can use it tomorrow, or even today, this afternoon, right? So this is my goal, to teach you something, to show how to do stuff that is running Postgres on Kubernetes, and to learn, so that you'll be able to learn, probably me too. So, first question. Who is here familiar with Kubernetes? Please raise your hand. Okay, a few of you. Who here uses Kubernetes in production? Okay, a few of you. And who uses Kubernetes but just for testing purposes, evaluation purposes? Okay. All right, so not a lot of you are familiar with Kubernetes, so we'll definitely start with that. And some of you use it in production, so you'll all be able to probably correct me. Anyway, so let's get started then. Well, first things first, a little bit about myself. Again, my name is Álvaro Hernández, or Álvaro, whatever works for me. I'm used to that. And I see my role mainly as an R&D person. I like to do research. I like to try to understand where the Postgres market is going, where the users are demanding new ideas, new help from the Postgres environment ecosystem. And this is what I mainly do. In other words, this is the nice way. The reality is just them doing crazy things all day. And some of them may make sense, some of them may not. For example, a few years ago, I did a project called TorDB, where we created a software to map what is MongoDB documents in real time to Postgres tables, and create tables dynamically, create columns dynamically, and take JSON documents coming from MongoDB as part of our replication stream and dump them into Postgres. Or another project I worked on, which is basically the Billion Tables project, where the main idea was to create 1 billion tables, so 1,000 million tables in Postgres. Empty, but at least 1 billion tables. What for? Oh, just to test Postgres scalability. It was a 6 terabyte database with 0 bytes of data. It was all metadata. You know, so this is the kind of things I try to do. More formally, I'm the founder and CEO of a company called Ingress. Ingress means on Postgres. So it's easily to guess what we are working on throughout the day. And other than that, I try to do a lot of community work. I organize a Postgres conference, which I hope you will all be able to attend this summer in June in Ibiza, in Spain, on the beach. It's not a bad place. It was an outstanding conference last year. This is going to be the second edition, so I definitely recommend you to attend this conference. If you want to check it out, pgibz.io. And I also run the Postgres community in Spain, and I try to speak at conferences like this. Last year, I did around 15 talks, and this year, I'm going to reach my 100th talk, speaking at tech conferences. So I'm boring. And I also was appointed recently as an Amazon data hero, which means I deal with data in some weird ways, apparently. Anyway, so enough about me. Let's talk a little bit about Kubernetes then, especially because most of you don't know what it is. Let me try to explain what it is, because I'll try to avoid all buzzwords, all classical definitions, all definitions that will let you the same way as you came here. I'm going to try to really explain you what it is and what you can use it for. Let's see if I get it. But this is a non-classical introduction. I haven't seen anyone define Kubernetes as I'm going to do it today. That means I will very likely be wrong, but maybe it will help you try to understand what it is. So let's start with this definition. And for you who know Kubernetes, correct me if you feel that I'm wrong. So to me, Kubernetes is an HTTP server. Okay? Well, that doesn't tell us much, right? There's plenty of HTTP servers over there. So what's special with it? Well, it's an object HTTP server. Okay, what does it mean? An object, are you talking about a REST API? Well, actually, it's also a REST API. So yes, you can expose objects, resources in REST terminology. And yeah, it's that for sure. But why this is important? Because nobody starts talking about Kubernetes this way. They say different stuff. So why I'm explaining to you that it's an object HTTP server. Okay, so the key here is that Kubernetes, it is an object HTTP server, and that exposes objects. And these objects, you can obviously interact with them, like with any HTTP usual verb, right? You can create objects, you can modify existing objects, you can delete existing objects. So far, this is nothing different from an HTTP REST API or whatever, right? The key here, and it's a pattern that is enforced across all Kubernetes, is that when you create or modify or delete these objects, some actions will be triggered. The object themselves, they really don't have any meaning per se. What is important is that when you touch these objects, there will be some actions on behalf of you, behind the scenes, that will be executed. So in reality, what Kubernetes is again an object HTTP server that exposes these objects as a facade, as an API with which you interact with, and then operations will be performed on the real thing that is behind the scenes. In Kubernetes, this is typically containers, but it's definitely much more than that. It's also storage, it's also networking. So basically, this is what it is, Kubernetes. It's an HTTP API, which exposes objects. Objects, let's talk about paths, URLs, right? So it exposes URLs. And whenever I send HTTP commands to these URLs to create, modify, or delete objects, this is going to trigger actions on containers, on storage, on networking. This we'll see later. This is also called the operator pattern. But let's think about this as an API. And the interface to this API is HTTP. So pretty simple stuff, right? But it will trigger very powerful actions behind the scenes. Okay, so let's try to illustrate this a little bit. Maybe it's a bit small, but here you can see an URL exposed by Kubernetes. And this is the API server where Kubernetes actually contains several servers, several daemons running. One of them is the HTTP API by itself, right? And you can submit these objects. We'll see now how to do this actually, right? To a given URL, and they will perform some actions. Most of the time, these actions involve persisting data on a specialized database. And this database is, on Kubernetes is etcd. Who are you familiar with etcd? Can you raise hands? Or Consul or Zookeeper? Okay. So, well, etcd is a DCS, it's a distributed consensus store, which means that runs on several nodes, it's a distributed database, and it is consistent by definition, which means any write operation, any read operation you direct to etcd, you'll get a consistent view of data, which means it doesn't matter where you read, where you write, you will always see the same consistent information with respect to the order of the operations you're performing. In other words, you can really trust this data store to store data there. But it's a key value data store. So it's useful for small amounts of information. And what is the amount of information that is stored there? These objects. So in other words, Kubernetes is an HTTP API that when you create or modify or delete these objects, it's going to store them, it's going to persist them on this distributed consensus database called etcd, where when you connect, any node will see the same information. And then, depending on the case, we'll perform some actions on the containers, on the storage, or on the nodes. And so if it's an API, it should be documented, right? Definitely, definitely. So if you just look on a search engine for Kubernetes API, you'll get to the official documentation for the API, which looks like this. And here you can see the verbs on how to interact with this API. Now, good news is that there's a couple of options to interact with Kubernetes. One is any HTTP client, because again, it's an HTTP API. You can use curl HTTP or whatever other, or obviously programming languages to interact with the Kubernetes server. And this is very usual. Now, there's also a command line tool, and we're going to be using it today a lot, which comes with Kubernetes distribution, which is called kubectl. And with this tool, we can use YAML files to call this API. But at the end of the day, it doesn't matter how we interact with Kubernetes and how we interact with this API, we are going to be creating, modifying, or deleting these objects that, again, will trigger actions behind the scenes. And we're going to see this very practically, so bear with me for a moment. OK. Now, so this is more or less what it is, Kubernetes. Now let's try to explain a little bit why would you want to use it. And here let me take another small digression. I call Kubernetes the JVM of the architecture of distributed systems. So why is this? Why the JVM? Some people don't like Java for whatever reason. I love Java, but it doesn't matter. So what is the JVM? The JVM is an abstraction layer. This abstraction layer provides us with, again, an abstraction over several layers underneath. For example, and most prominently, the operating system. When you write a program in Java or any JVM-supported language, for that matter, it doesn't matter if you're running this on Mac or Linux or Solaris or Windows, if you want to do it for that, any reason. And you'll get the same experience. So what the JVM does is there are some primitives that are operating system dependent, like how to open a file, how to open a socket. And those are abstracted away and then presented with a single API for us. Well, so Kubernetes is pretty much the same, except on a totally different landscape, the distributed system scenario. So Kubernetes exposes this API that I was referring to before, these URLs, these objects. And these objects will create these actions related, again, to containers, or to network, or to storage. And those are independent of our actual storage or our actual network. And this is key to many problems. So, because if we go to clouds, each cloud is different. Maybe all clouds exposed a network disk, which offers some persistency mechanism, but they're all different. If you want to create those disks, you need to use different APIs. If you're on Yandex Cloud, you'll use one API. If you're on Amazon, you'll use another API. When you want to create a network load balancer, same story. All clouds offer a network load balancer, but they're called differently, they have different parameters, and their APIs are different. So you need to use different commands, different SDKs, different tools, different programs to create them. Now let's go to on-prem. When we go to on-prem, the case is even more complicated. Network load balancers, yes, there are, but sometimes they're hardware, like F5, they're appliances. How do we manage them all? And what about the storage? Storage is a huge world, right? On any environment, they can have different storage. So is there any way in which I can describe an infrastructure that is going to be independent of the underlying real infrastructure? Is there any way in which I could expose compute, storage, and networking, which are the basic building blocks for any application, in a way that will not be depending on the environment? Yes, and that is Kubernetes. This is one of the main virtues I see of Kubernetes. That's why I say it's like the JVM. As long as you program against this API, what is the storage is used underneath, or what network is used underneath, or how containers are deployed underneath is not my problem. Might be the problem of the Kubernetes cluster administrator, the same that running a Java program is this will be the problem of the person who maintains and deploys the JVM and configures the JVM. But for me as an application developer, as a user, as a consumer, it doesn't really matter. So this is key, because Kubernetes makes environments homogeneous. And now I can deploy applications in an homogeneous way. Applying to Postgres, which is our use case today, this means that we can create a Postgres distribution, and I will also talk about that today, that will run with a single code base, a single Postgres distribution will run on any Kubernetes environment, whether it runs on Amazon Cloud or Yandex Cloud or on-prem, it will run exactly the same. And only the system administrator will need to configure it in a way to install Kubernetes on your specific environment, which, for example, in cloud environments is pretty trivial, and they even offer managed Kubernetes services. So, again, it is an API on which I can create applications in a homogeneous, independent way from the infrastructure. And this API gives me, and we will see many examples of this today, very powerful APIs to create things like storage nodes, to create volumes, to create network services, DNS, load balancers, obviously containers, which is all what is this about, right? So we'll see many of these APIs. It offers a lot of APIs here. And the good thing is that because I have all these exposed APIs, all the network, all the storage, container execution, and a lot of automation, I can create a fully automated Postgres install, a fully automated Postgres cluster. We're also going to see this today. Okay, enough talking, enough slides. Let's go to the black screen. Any questions so far? Yes, please go ahead. If you don't mind, I think you've got a microphone. If you can just repeat the last part of your question.
I'm sorry, I repeat. Please tell about how you wait to set up read-write many storage for the pods of Postgres on the Kubernetes.
Okay.
What's the way? And
okay. Yeah. All right. So the way Kubernetes exposes storage is an abstraction, as I was mentioning before, right? Kubernetes exposes many abstractions, and one of them is the storage. And the storage has several characteristics. Some of them are depending on the environment, but this is, again, abstracted away by the API. And supports many kinds of storage because Kubernetes has this concept of plugins. And you can use plugins that expose very specific characteristics of a given storage over a standard Kubernetes API. So regarding your question, there's three main modes in which you can expose the storage to the containers, which is whether you can have one writer and many readers, or many writers, right? So the question was about this last one, many writers, right? Okay. So obviously, there's no magic there. If we expose an API over a storage which allows for multiple writers to operate simultaneously, what we need to have under the hood is a file system that allows for multiple writers, right? It's not going to take anything like a volume exported by a SAN and make it by magic, again, able to be written by many nodes at once. So in other words, what we need behind the scenes is a network file system, distributed file system, NFS, CA, PHS, CEFs, or Lustre, or whatever. There are several distributed file systems that support concurrency and support distributed operation. So we need this for sure. So it doesn't matter how it is exposed. It's going to be exposed as a regular volume in terms of Kubernetes API, but we need to have a distributed file system behind the scenes. Now, regarding to Postgres, so how does Postgres work with distributed file systems? Theoretically, works. Practically speaking, it's a different story. For example, it is not very advisable in general to run Postgres on NFS. While NFS is theoretically correct and theoretically will run a Postgres cluster well, there may be consistency problems if you're not using the hard mount options, and there might be some communication failures at some point. Data may get corrupted in a pretty badly way, and I've seen this several times. So I will totally not advise to do that. It is possible to do that and theoretically correct, but I will definitely not advise to do that. And there's very few experience with running Postgres on other distributed file systems that are not NFS. So I would say it's even less advisable, which in other words means I would recommend you to run Postgres with a storage that is more classical. Typically, I would say a network disk, having one disk per Postgres node. Yep. Okay, more questions? It's all good? Are we all clear with what is more or less Kubernetes? Yeah. Okay. So if the storage is defined with multiple writers, read write many it's called, then yes, it could be shared, right? It could be mounted, read write by many containers. So definitely multiple can write there, but it needs to be a storage that supports that under the hood. NFS? Yeah, any cluster file system will support that. There's actually on the Kubernetes documentation kind of a table matrix explaining which file systems, which are in turns supported by Kubernetes, support the different access modes. But for Postgres, I would say this is not interesting at all. Maybe you could use something like this for taking backups. That makes more sense. But not for the primary storage of the database, not for the PG data, right? Oh, no, absolutely not. You can definitely create Postgres clusters. I'm going to show that today. But these Postgres clusters will be the same way you would build them without Kubernetes. How would you probably build a Postgres cluster that you'll have several disks, one per VM or host or whatever, right? So we'll do here the same. We'll have one disk per Postgres node. Okay? This disk could be also a network disk, and actually it's recommended because if you're running on a network disk, this volume is not attached to the node, and if the node fails, you'll have this disk there. You can reattach to another container, and this is trivial operation on Kubernetes. It could be fully automated. But you can also run on local volume. There's many options on Kubernetes for doing this. More questions? You want to go fast to the demo, right? Okay, let's do that. I'm gonna take a seat if you don't mind. So I need to type a lot. Okay, so. Okay, otherwise I have it locally. No big trouble. Is Kubernetes? Sorry. Analog of Hadoop. No. So Hadoop is basically data processing, right? You can store large amounts of data and run jobs to get queries, basically, of the data. And Kubernetes, from this perspective, is infrastructure. How to deploy workloads, how to deploy containers. Okay, so the question is Kubernetes a cluster, and what are the benefits of using Kubernetes, right? So yes, Kubernetes takes nodes. It could be hosts or it could be virtual machines. It doesn't matter, and put them together in what is called a pool of resources. So let's say you have 3 machines each with 4 cores and 4 gigabytes of RAM. Kubernetes will say, oh, you have 12 cores and 12 gigabytes of RAM. And here you can run containers, which will be a web server, a database, and put them into these resources. So what are the differences with using standard storage? Kubernetes has normal storage behind the scenes, right? So Kubernetes has the storage you have in your cluster. In your cluster, you have a Sun server. You can use that in Kubernetes. You have NFS. You can use that. You have local disks. You can use that. The difference is that whatever you have in Kubernetes, it will be exposed as a single API. And you can create programs, and a program that will run on local storage or network storage in your environment may only be one line change.
Can you say about example of utilization this technology?
Yes, actually, that's exactly what I'm going to do right now. I'm going to show a lot of examples on how to create containers, how to create storage, how to create DNS entries for services, and we're going to do a lot of magic. So you'll probably see enough examples. Otherwise, let me know. Yep. All right. So. Good. So the first thing we're going to do is, who's familiar here with Docker? Let's start with the very, very basics. Yeah, okay, a few of you. Okay, a few more coming. Okay, so just to make it clear, Kubernetes works with containers. And container is I'll explain this more detail later, what exactly it is a container. We'll get into the technical details, but a container is a way of packaging an application. I create an image which contains a file system image, and within this image there's going to be one or more binaries. And when they are run, they will run a process or a process hierarchy inside of this container, right? So a container is a way of packing an application, and because I pack all the application, all of its dependencies, everything that comes with this, I can run this container on any environment the same way, and I will get the same results. It doesn't matter if I'm running on top of Ubuntu, on top of Debian, on top of any other Linux distribution. It needs to be Linux anyway, but because I pack everything together, I get the same results. It's kind of a VM, but I hate to say this because it's totally different from a VM. It is an abstraction layer over a process or a process hierarchy, and its IP address space, and it's a process space, but it can get the same results. So I can run a container on my laptop, as I'm going to do right now, and this is going to create a container image, for example, of Postgres, which I'm going to use, and this is going to create a container on my laptop, which will run Postgres. If I now go to my production server and run the same command, I will get exactly the same results. So it's a way of deploying applications. Let's start with the basics. Let's run a container first on a classical environment, such as similar to Docker, and then we'll go to Kubernetes, just to do this as an introduction, right? So I use, I don't know if you can also see this. Yeah. Okay, so I use a container environment in my computer called Podman, which is built by Red Hat, and it's pretty convenient. It's like Docker. Actually, it's totally compatible with Docker, except that it doesn't require root permissions. So it runs totally user space. By the way, all this is public. So if you want to access this code, I'll let you know the URL later on. Yes, there's another question there.
Why you use Podman but not classical Docker?
Because Docker requires you to run as root, and as such, it can have some security problems. If you're able to, if there's a bug, there's a security issue with Docker, you could become root over the host, whereas Podman runs in user space.
But as I know, it's not capabilities, same features. For
me, pretty much everything that I need, yes, it is provided by Podman. Yes, it's not 100% feature parity with Docker, but it's very specific things. If you're good without them, you're better with Podman because, again, it doesn't require any root privileges. Because after all, containers are processes. And you as a user, you can launch your own processes, right? And they can run over your permissions, your user IDs. So you don't need root for that. Docker requires root because it runs a daemon, which is a server, which receives the commands. But that was very likely a questionable design decision when it was made.
And you can recommend Podman for production?
Yeah, I do. Yeah.
Okay.
All right. So again, we're not on Kubernetes yet. We're on Podman containers. So how do we launch a container? Actually, it's pretty simple. So I use this command Podman. Then I'm going to say run. I'm going to give a name to this running container. And then I specify an image. The image is the container image. Where do I get this packaged file system which contains a process inside? By default, everything goes to Docker Hub, which is a repository for containers. Let me show you that. dockerhub.com. Thank you for your internet connection. And if you look for Postgres, for example, you'll see that here there's images of containers that contain Postgres, right? And you see you reference the image by name. You can also specify some tags, like 12.1. So for example, if I take this command and just say, okay, I'm gonna run this, and I'm gonna specify some extra options to run this as a daemon and to delete all the resources created by the container when the container finishes. So let's deploy a Postgres, in other words. Let's give this a name. Let's call it PG, or let's call it TMP. Let's say run as a daemon, and let's delete all the resources after this, and let's use actually Postgres. I'm going to use Postgres 12.1 version because I have it cached locally. Should be faster. Okay, it's going to the internet, whatever. Damn, should be local. Thank you so much for the internet connection. I cached the images. So anyway, what is happening here? This Podman command is, I'm telling, run this container. This container is a Postgres image. This image is by default stored on Docker Hub, Docker IO, it's the same, goes to the same place. And I'm just downloading this image, which contains the file system, which contains Postgres compiled inside, and which contains an entry point, and what is the command it's going to run when the container starts. So while all this is happening, it's going to take a bit. Okay. I'll run to the next command in the meantime. So I was expecting this to be cached. Actually, let me do that. I think it's, no, it's not going to be cached. Okay, I'll keep this running in the background. I'll show you the results later on. So this is going to run a container with the Postgres image, run a command, and then I can totally dispose it. When I'm done, I can dispose this command, and I'll be happy with that. Actually, let me do something else. Let's see what images. By the way, is the font okay? Can you read this, or you need it larger? Larger? Oh, sorry about that. Is this okay? Actually, I'll make it a bit bigger. Yeah, so we can see the. Is this okay? Yeah, okay. So let me list what images do I have here. Maybe I have some better image that is local here. Let's try to use that. So here I have a Postgres image, Alpine. Yeah. So let's try to use this one. 12.0, okay. So 12.0 should be local, and they should be faster. Okay, good. So this was local image. It went faster. So what happened here? I launched a container with a Postgres image, which should be running Postgres. So if I do podman ps, I see that indeed there is a container ID here created, which is running this image, and there's a command run Postgres. So what do I do with this? Actually, I have a Postgres server running already, thanks to just this command. I didn't need to download anything, to install anything, to configure anything. It magically ran. This is the beauty of containers. I grab a container image that someone published on the internet, issue a command, and now I have Postgres running on my machine. How do I do this? Now, I'm going to launch another command which will run inside of this container shell. So I'm going to get kind of an SSH. I'm going to get the shell inside this container, and I'll be able to check that there's a Postgres running there. So if I do podman exec on this container, and then a shell command, I get a shell. And if I do a check that there is a Postgres running there, I see there is a Postgres. And very likely, I'll be able to connect. I need to probably become, hold on, let me fire a bash shell. Yeah, better. So if I sue as user Postgres and I try to connect, yes, here we are. And this is Postgres 12 that I got. So again, with this command, what had happened is that Podman or Docker would have done the same, have gone to the internet, downloaded an image which contains Postgres precompiled, and run it. And then I have a Postgres server. So simple. When I'm done with it, I can just say podman ps and podman stop. I stop the container, and we're done. No more Postgres. So this is how you work with containers. Super simple, super convenient, and this image, it was built on Alpine Linux or CentOS or Ubuntu. I don't care. My computer is running Ubuntu. It doesn't matter. The image can be anything else. It will run perfectly on my computer as long as kernels are compatible. Okay, cool. Any question here? Let's jump into Kubernetes. Yeah, question.
На русском языке задам вопрос.
In Russian, if I may, please tell if you want to use some options of initialization of something else, not the ones that you have in container to initialize a cluster. Can you do that, for example?
If you want to create another kind of initialization of cluster, can you do it?
Like, you mean like a different initialization of the container?
Yes, to change some different parameters of initialization of Postgres.
Oh yeah,
in container.
Yeah.
You can.
Yeah, definitely you can do this, and we are going to do this in the next demos. Actually, if we go back to the page where we can download this image, there's documentation here. And here, in this documentation, you can see, for example, here, that you can pass environment variables to the container. And for example, if you pass a Postgres password or a Postgres user or initdb args, and you pass this an environment variables to the container, which you can definitely do, you will change these initialization parameters. And there's a demo for that. So we'll do this. But we're going to do this with Kubernetes. Not with Podman, but with Kubernetes, because it's even better. The way you would do this, by the way, there's an example here. I think. No, it's not. But anyway, we're going to see this with Kubernetes. OK, so any other question here? Yeah.
One question about Podman. Actually, I'm familiar with classical Docker, and I saw that you made the ps command in order to find the ID, and then use this ID to stop the container. You gave the container name TMP. So you probably could have used that.
Yeah, I should have used that.
In classical Docker, is Podman the same?
Yes, yes.
OK, that's what I wanted.
I just
Thank you.
picked the ID. Yeah. So Podman, by design, they totally mimic the Docker interface. Unless some feature is not implemented, should be pretty much equivalent. Yes, I took the ID. Took the long path. Forgot about the name. OK, any more question? Let's jump into. OK, one more question.
The adequacy of resource for its development.
Пожалуйста.
How to see the status of the container? Access the adequacy of resource for its development.
OK, yes. So did you see this ps command I executed before? So this Podman ps or Docker ps will show you whether the container is running or not. This is the most important thing, because the container is a process. If the process dies, the container dies. OK? And then if you mean about storage, if it's executing, sorry?
If this execute one how, two how.
Yeah. So again, with PS, you can see if it's running or not. If it's not running, actually it will die. OK? Because the container is the process. Now, you can launch several containers with the same image. You will see several containers with that image running also with this command.
For example, the process of backup, its status 50% finished.
OK. Well, you will see with Kubernetes. Again, this is just a demonstration of containers first. When we're going to jump now into Kubernetes, you will see that when you launch like a pod, we will explain what is a pod. There's a status field. And if your application wants to expose the status of a job, for example, you can use this object to communicate back. But
how we can monitoring what resource needing to run our container?
OK. So first of all, you're going to see also right now how do you specify what is required for running a container. You will specify this in Kubernetes. You will say which storage, which images. You can specify the CPUs, the memory you want for the container. And this, you can limit this. And then with Kubernetes APIs, you can monitor this very easily also.
How it works automatically?
It really depends on your configuration. So you'll specify the storage. You'll say, I want this number of CPUs maximum. I want this memory maximum. And this will be honored by Kubernetes. Automatically, from that perspective, yes. Yeah, let's see this with real objects. Because you're going to get a better feeling of how, yeah.
You say that if we run two same containers, so we have two processes. Yeah, but Postgres container is not stateless container because it's work with data, and if we have two same container running on same PG data, we have some conflict.
Oh, yes, that's a disaster. Yes, we're going to see this. I have examples on Kubernetes on how to manage the storage. So first, we're going to run some containers without persistent storage. And then we'll use some examples with persistent storage. And we're going to even create that conflict.
How we can, what help us don't do it?
Well, I mean, definitely you need to understand what you're doing. But in general, it's pretty simple. But I'll show you later. Bear with me for a moment, because I'm going to show you examples on all this with explanations on how to do this in Kubernetes. We're going to do non-persistent, so ephemeral storage. We're going to do shared storage, which will corrupt Postgres effectively. So pretty bad idea, but also show that. And then how to do it correctly. OK. Good. So let's move on to Kubernetes. So this is Podman, this is Docker, it doesn't matter, this is not Kubernetes, it's just how you can do this very simple with containers. Docker and Podman make this process very simple for running a single container. But very likely we're going to want to have more than one container. Maybe we want Postgres, maybe we want PG Bouncer, maybe we want something for backups. Those could be totally different containers. And then we're going to want several replicas. Right, a master and 3 replicas. So this means like a total of 12 containers. And we want all of them to be wired together and act together, each one with its own storage, relating to all your questions here. This is much more complicated to do with Docker or Podman. So this is where Kubernetes really helps. And I'm going to show you how it helps us wire together all these pieces. But let's start from the very basic. How can I deploy a container on Kubernetes? Well, actually, let me explain you before that in Kubernetes, you don't deploy containers directly. You deploy pods. And what is a pod? Well, a pod is pretty much the same as a container, except I can have, as part of the same unit, more than one container together. So think that in Kubernetes, I have nodes. Could be virtual machines, could be physical machines. And on each of these nodes, I'm going to run these workloads, these pods. They can run on any server. When I say to Kubernetes, hey, run this workload, it will choose a server based on capacity, based on other characteristics, based on some specifications, and it will run it there. I don't know. I don't even need to know which particular node is going to run. I'm not going to say run on this node with this IP. I don't care about that. Kubernetes is, by definition, declarative. I specify what I want, not how I want it. And so a pod is something that you cannot divide. If I have 2 containers within the same pod, they will run on the same node. And this is very interesting for these containers to collaborate. Let's say I want Postgres alongside PG Bouncer, which is a typical good practice in Postgres land. And I want them to communicate via Unix domain sockets, for example. They need to be together. They need to be part of the same unit. And this I can do. So, pods. For now, let's forget about that. I'll get into this a little bit later. But a pod is the unit of deployment in Kubernetes. And within one pod, I can deploy 1 or more containers. So again, let's see how to do this. If you remember, I was saying that this is an HTTP API, right? So I can write a CRL curl command like this to send the necessary request to the API server to create this pod. But there's a simple way of doing this, and this is the way we're going to be using today, which is to use a command line tool called kubectl, which allows us to run JSON or YAML files. I'll be doing YAML today. Sorry about that. But this is very common on Kubernetes land. Some YAML files to specify the actions I want to run. So, how it looks like. Sorry. Part 1. All right. Good. So this is how you create a pod on Kubernetes, a very simple one. And as you can see here, instead of running a command line, I create a YAML file. We'll always use the API version first, which is Kubernetes is on version 1. So this line is going to be always the same. And second line, this kind, is the type of object I want to create. Remember that I said that Kubernetes is an object server? OK, this is the object. Here I want to create an object of type pod. What is a pod? Again, one or more containers I want to run. There's always a metadata field where I specify, metadata, and the name is a compulsory field. What is the name of this object? Objects have a name. This is the identity of the object. So they need to have a name. And this name is unique. We understand what is a unique constraint, so no issue in this room, right? And then there's the spec. The spec is the specification of the object I want to create, and this is object dependent. Each object have their own types, their own spec, and they're documented as part of the Kubernetes API. So how does the spec look like for a pod object? Well, pretty simple. I say containers. Remember that a pod can contain one or more containers. And this on YAML is obviously an array. And I specify the image and a name for this container. Because within the pod, there could be more than one container. I specify also a name. Here, the image is the URL to the Postgres image I want to use in this case, the official Postgres image and a version. I'm just hard-coding here the version and the URL because I have them locally cached, so I avoid wasting your data, and so it will be faster operation. So this is all you need to do on Kubernetes to run a simple pod like this. And now we're going to use the kubectl command to run this, and this will create the pod. In reality, what will happen is much more complex. This YAML will be transformed into an HTTP call by this kubectl command. We'll call the API server. The API server will create this object. We'll end up with a URL. And then there's someone else in Kubernetes land listening on new objects of type pod being created. And when an object of type pod is being created, it will trigger some other actions to actually download this image and run the container on a given node which has the desired capacity. So let's see how it works. So I use this command line tool called kubectl. First of all, let's check that there's a cluster running. There's a cluster running on my computer. It's a local cluster, only has one node. Okay, I could have several nodes here, but there's at least one node where I can schedule containers so I can run containers. So how do I do this? I just say apply and the YAML file. This is all I need to do to create this container, this pod. Let's do that. Cool. Looks like the pod has been created. How do I check this? I check the pods. Yes, I see that the pod is here. And let's look at the object. The object that has been created should contain the data that I created plus some extra metadata. Let's check that. Again, font size is OK for all of you? Yeah? All right. So if I describe this object, let's page this. Yeah, I see that there's the name is the name that I associated with it. There's some other metadata here, the startup time, some annotations. I don't care about this right now. There's an IP associated with it. Kubernetes does automatic IP allocation. And this is an IP. Doesn't matter right now which IP address is this. There's a few information here. OK. Volumes, you see, volumes. There's some volumes, but there's no persistent storage here yet. We'll see that later. And then there's events. These events is the information I was referring to before. You can use to post status information about the workload of the container. Here it says, first of all, it was scheduled to run on Electro. Electro is the name of this computer, which is the name of this node where it is running. Then the container image was already present on the machine because I pre-downloaded it to have it locally. And then was able to create the container and then to start the container. Pretty cool. So now you believe that I have a container running here. So if that's true, I should be able to connect to this container. And let's see if there's a Postgres running there. So similarly to Podman, I can also execute another command within this container. Let's do that. So I'm going to execute on the pod called pod PG, on the container PG. If you remember, within a pod, there could be more than one container. And then I'm going to run the command bash to get a shell. Cool. Apparently, I'm inside of the container. If that would be true, I should be able to connect to as a user Postgres, which is a user with which the database is created by default on this container image. I should be able to connect to Postgres. Excellent. This is Postgres 12.1, because I'm using the image Postgres 12.1, if you recall, from the YAML file. Actually, when I run with Podman, I run 12.0, because that's the image I happen to have around. So you're seeing, just with one command, I'm running different Postgres versions on this machine. That's pretty cool, because I'm running containers. And OK, let's create something here. Let's create a database called A. And let's, yeah, database is created here. OK, so let's log out of the container. Now, Kubernetes is also very cool how to operate with this. I can now destroy the container pretty easily. So let's say, for example, kubectl, again, get pods. Here I have the pod. Let's say delete pod, and then the name of the pod. This will delete the pod. And that's it. Done. Again, for you to remember, this is all that I had to type. This YAML file. And this will create this pod for me. What is also cool about this mechanism of what we're seeing here is that we are creating infrastructure. In this case, we're creating a Postgres database with a file. I'm not typing any command. Well, I'm typing this apply command. But I'm not installing anything. I'm not creating anything. I'm just grabbing an image built by someone from the internet. In this case, the official Postgres image. And I'm writing a small descriptive language file and executing it. And I get the container. I run my Postgres server running. This server is yet not very useful. We're going to get into that. But actually imagine you just put this on a Git repository. And when you do a commit on the master branch, you set up a trigger that will run this command kubectl apply. And will apply this file. You'll get automatic deployments. Whenever someone changes this file and is committed on master, it will create a trigger. It will run on the cluster. It will deploy automatically. This is called GitOps, operations driven by Git. And it's a pretty cool mechanism. You can definitely do this with Kubernetes very easily, because all your infrastructure is going to be YAML files. Now, there's a small problem with this container. Where's the storage? You were asking before, right? Let's run it again. So if I apply the same stuff, and I exec and sudo Postgres, and list the databases, there's no A database there, right? It's gone. Why is that? Because I didn't assign any storage to the container. So by default, the file system inside a container, this also applies to Docker or Podman, it is ephemeral. It will disappear when the container exits, right? So we need to take some extra steps to have some storage that will persist, because this is something we want for a database, right? OK. So let's see how to do this and other things. Any question before that? We're all good here? So you can all now deploy a basic Postgres server on Kubernetes easily?
Can we get this YAML file somehow?
Can you get the YAML files?
Yeah.
Yes, they're all, these ones?
Yes.
Yeah, I'll share the URL later. They're all public.
Just to be in synchronization with you.
They,
just to be in sync with you.
Oh, yeah. OK.
Just in time.
With pleasure. Yes. So there. All right. So let's move on. Okay, let's delete this. Oh, I closed the shell. Sorry about that. All right. Delete pod. Cool. So we have deleted pod. Let's move on. So this allows us to run a basic pod. Oh, also interesting. Let me create it again. So here I have the pod. I already used the describe command to get more information about this object created, which I showed you before, which shows includes the IP, the storage, and these events, which is interesting to understand what is happening with the container. Right? All this I get with the describe command, or in this case, describe and the pod. I was describing all of them, but this will bring me the information for this specific pod. Good enough. This is also interesting. This is a container, right? And another thing that Kubernetes does is that by default it captures the logs, the output of the container, and so most tools that run on a container write the output to the standard output. This standard output is captured by Kubernetes and presents me as a specific command, which is logs. So actually, I can get the logs from this pod. And yep, I can see that this is the logs for a Postgres starting. I see that it creates a cluster at the beginning. That's an initdb. It's using it in varly PostgreSQL data. And it says some logs, and then the database at some point is ready to accept connections. So I get the Postgres logs because this container image is designed with this in mind. So it's dumping the logs to standard output. This has been captured by Kubernetes, and it's presenting it to me with this command logs. Cool. So I can create a container. I can run it. I can see the logs. I can describe the object that's being created by Kubernetes, and I have a non-persistent Postgres database. Let's delete it. Let's move on to the next stage. So let's make the data persistent. There are several ways in which we can make the data persistent in Kubernetes. One of them, not the one I would recommend you to use, but for completeness and because it's quite simple, let's use the mechanism called host path. So host path is pretty simple. We'll expose a volume, a mount point to Kubernetes, to the pod, which in reality is just a folder on the host system. So the host system is the node where the container is going to run. And there I can have a folder, and this is going to be presented as a mounted folder inside of the container. And this is going to be persistent because this is going to be independent of the life cycle of the pod. It will be on the host system. Why this approach is not recommended? Because it depends on a given node. And one of the mantras of Kubernetes is that I don't depend on any node. I said before, I want to schedule a workload. It will be a Postgres database. I don't care in which node this is going to run. But if the data is local to the node, I do effectively care where this container is running. And if this node goes away, my data goes away. My container will not be able to access the data. But let's show it as an example because it's pretty simple. So what do we have here? Okay, I hope this font's still okay. So pretty much the same. This is the same, except here I'm using this extra part. This is what has basically changed with the previous file. So let's look at this part first, the volumes. So here I see that the specification before contained only one field called containers. Now there's another field which is part of the pod specification, which is volumes. Here I can specify one or more volumes. So this is an array. And for each volume, I specify the name. In this case, let's call it PG data because it's actually where I'm going to store the PG data for this container. And the mechanism. The volumes have many possible types of volumes. I could use a volume provided by Amazon Cloud, by Google Cloud, by Yandex Cloud, by local storage, block devices, NFS, SEVs files, distributed file systems. Many, many types of volumes I could use here. Here, now, I'm going to use this one very simple, which is called host path. I just need to specify the path of the directory where this folder is going to be created. and this is going to be exposed as a mount point inside of the container. How do I specify this? Once I have created the volume, or I specified the volume, inside the container, I specify a volume mounts field. And here I just need to reference the same name I created when I created the volume, and specify where do I want to mount it. Where do I want to mount it? In varly PostgreSQL data, because this is the place where this particular container image is placing the Postgres PG data, the data for the database. All good, let's give it a shot. Okay, so if I do kubectl apply f and this pod, cool. It says that the pod has been created. I'll make the font a bit bigger. Again, let's verify that. Yes. Let's look at the describe information. There should be more information about the volumes right now. In fact, if I scroll down, here I see that it has a mount point, which indeed is varly PostgreSQL data coming from PG data. And PG data is also described here as a volume as part of this pod, which is of type host path. Here it says bare host directory volume, and it's under /PG data, TMP PG data. By the way, just for the sake of correctness, let me delete this for a moment. Just to make sure that that folder doesn't exist. Before, just one moment, I'll repeat this operation. Okay. I just want to make sure this folder is absolutely empty. Okay, and let's run this command again. Again, kubectl apply -f, and then the YAML file. This will execute the resources I want to have on this YAML file. Let's do that. Create it. Again, I'll get the describe, and I'll see the var lib. It's here. Cool. So it looks like it's mounted. Let's do an exec command again to connect to this pod, and we'll see that there's it's actually not shown here as mounted, but apparently this volume has been created on PG data, varly PostgreSQL data. Let's do that. Let's do something. Let's create some data inside of the database. Let's delete the container. Let's create a container again, and let's see if data was persisted. Before it wasn't, because we're using just ephemeral storage. If my theory is correct, and you're using persistent storage here based on host, if the container gets scheduled on the same node, I only have one, so I know it's going to happen, it will pick up the same data. So again, let's connect to this user Postgres. Let's connect to the database. Let's create, let's call it PGConf.Ru in this case. And let's exit the container, and let's delete the container, the pod. Once it is deleted, I will see that there's 48 megabytes of files created there. That's a Postgres cluster initialized plus another extra database. And right now there is no pods running. But if I create this pod again, because it's using this host path, should have the same data there. Yep. So we see the database is there. So in this case, what we have done, and I'll get back to the config file again. Let's delete this first, just to have everything cleared here. Okay, let's pass it to background. So by adding these last parts here, sorry. By adding these lines, what I have effectively created is, first of all, storage on the local node of the type host path, which again, I don't recommend this for production, but it's quite handy for this kind of demos, which takes a local directory on the local file system of the node and exposes this as a mount point inside of the container on the path I want. And that's it. This is persistent. This survives across container restarts, because otherwise the storage of a container do not survive restarts. Sounds good? Okay. So then let's improve over this. What is the next step? So the next step is to try to make a volume for the container which is not tied to the host itself. In this case, if I would have, if I run a cluster in the cloud with many nodes, I don't know where the container is going to be scheduled. I could actually force Kubernetes to schedule the Kubernetes on the particular node that I want, but what if that node dies? I will lose my data. It's better to use network-attached storage and like typically, actually I use the word terms network-attached storage, but I was thinking more of sandblocks, and attach this to the nodes. And this is a much better mechanism. Let's see how to do that. Any question before that?
Álvaro. Álvaro, we have 15 minutes to coffee break.
Yeah, thank you.
And what happens if we run two containers in Kubernetes with one mount pass and one host pass?
Yeah.
What happens?
Well, the same stuff as if you would run a Postgres with the same, two Postgres instances with the same PGData directory. You'll corrupt them. That's yes, that actually, and we're going to do that. There's one example, indirect example of this. We will see that.
In future, we will describe how we can avoid the situation.
Yes, yes,
Thank you.
absolutely, absolutely. Okay, so let's move on. Let's see how to create a volume that is not tied to the node, in which case it could be a remote disk, typically in the cloud, so it will be a remote disk, and then we can attach this to any node storage. It will be much more convenient. So next step is to use what is called persistent volume claims. So this belongs to the category of dynamic persistent storage. So what is a persistent volume claim? Sometimes Kubernetes has a lot of these abstractions, like anywhere, they get too far. So in Kubernetes, we have the volumes, which we have seen. We have used a volume of type host path. But then let's say we want a persistent volume. Again, the concept of a persistent volume is something that is, which life cycle is independent of the life cycle of the node, because nodes are ephemeral. They can also die. So persistent volume is typically a representation of external storage, external to the node, typically. And Kubernetes has the two layers of indirection here. One called the persistent volume itself, which is really the volume, and what is called the volume claim. A volume claim is kind of a pointer to a volume. It's a request of a volume. It's an expression of, hey, I want to have a volume of 10 gigabytes created on this storage class, let's say. And I'm going to explain what is a storage class right now. And then once you have your claim, you say to Kubernetes, hey, I want to execute this claim, so I'm requesting for this volume, please give it to me. And if there is enough resources, Kubernetes will create the volume for you, will provision it, will point your claim to that volume, and you will be able to use it. So what is a storage class? And I know there's a lot of names here, but so a storage class is a name you define. It's another Kubernetes object called this kind. It will be a storage class, which you can create, and you assign a name and a type of a storage, a pool of a storage. Typically, you can have there. Let's say you're on Amazon Cloud and you're using EBS. You can create a storage class which will create volumes dynamically from EBS. EBS is the network disk of Amazon Cloud. And that's it. You call this storage class EBS, and then whenever you want to create a volume, you create a persistent volume claim against this storage class called EBS, and then you specify the size. And with this claim, Kubernetes will call to the Amazon APIs behind the scenes. You don't need to do anything. We'll provision the volume for you, and we'll attach it to your pod. Sounds complicated, but it's so much easier. So let's see the code first. So here we have two files. We don't have anything here, right? Good. So now we have two YAML files. One is to create a persistent volume claim. So again, remember that Kubernetes is an object server, has objects of different types. Here we have another type. We have seen the pod. Now we have a persistent volume claim. This is a request to generate a volume. Again, metadata name is always compulsory field. I specify a name for this claim. And now the spec. Again, this spec is dependent on the type of object I'm creating on Kubernetes. And in this case, for a persistent volume claim, I need to specify resources section. Then with the resources, what I request, in this case, I'm requesting a 1 GB volume. This is the access mode. This is the question you were asking before over the type of access modes. This is going to be a volume from a network device, which is not a distributed file system, so I can only allow for one writer and also one reader. So this access mode is going to be read, write once. And I need to specify what is the storage class name. The storage class could be environment dependent. Typically, there is one called default, but it's not always. On my installation, the Kubernetes cluster I'm running on my laptop, which is called Micro K8s, doesn't come with one called default, but comes with one called Micro K8s host path. Yes, internally it's based on host path, but I should not care about this. How do I know which storage classes do I have on my cluster? kubectl get storage class. It will tell me that there's a storage class called this. So what is a storage class again? A storage class is a pool of storage. It's a name from which I can create claims to request volumes. I could have, let's say I have a really fast SSD network disk. I could create another storage class called fast, which will be a pool of storage based on a SAN controller, which will based on SSD disk. And then if I want to create a disk based on SSD, I will say in this file, instead of this, I would say fast. And that will provision the volume from this SAN device. And again, from my application, from my perspective, there's nothing else I need to do. It doesn't matter that behind the scenes, this is running a CSI plugin, which is a storage plugin that uses a specific API for this hardware SAN, which uses whatever API. As long as there's a plugin for it, my approach to this is just I specify the name. So I have this storage class that exists, and I'm going to create this persistent volume claim, which again, basically means, all this file only means is, hey, against this storage class, which is a pool of storage provided by the cluster, allocate a 1 GB volume. Let's create it. Same mechanism. Okay, created. If I get this persistent volume claims, I can see that here's my persistent volume claim, and it's bound, which means it's already found. It was possible to allocate this 1 GB file on the volume, on this storage class. Good. So I have apparently a volume pointed by this persistent volume claim. Let's use it. To use it, I have this small variation of the file we had before. The only change here is that instead of using host path here, I'm calling persistent volume claim. And I say, I want a volume called PGData, which is using, is referencing, a persistent volume claim of name, the one that is specified before. Okay? So now if I create the pod, I see that the pod is being created. I will also should see a volume. Sorry, persistent volumes. Yep. So here I see that there's the volume created, because there's a persistent volume claim and a persistent volume associated with it. What all this means, even though it might sound a little bit complicated, is that now we have persistent storage for our database, which in this demo case, it's coming from local storage. But if it would be on any cloud or any other environment, this could be network storage. The only thing we need to change for this to make it network storage is change this, this name. For example, if I am on Google Cloud, there's one storage class by default that exists, which is PDSSD. That is persistent disk on Google based on SSD devices. I just changed the name this, and this will create transparently a network disk, and this will have a life cycle totally independent of the node of my containers and will survive any restart. let's try this. So actually, let's just connect to the container. Let's create some data, and let's check that it indeed survives. Right, so here we have the database. Now let's exit the container, let's delete the container, and let's create it again. Because it's relying on the same volume, it should survive. Okay, apply. There we go. Okay, and this volume, again, is persistent. If I exit the container, delete the pod again, and still list the persistent volume, I can also use short names. So PV is persistent volume. I see that the volume is still there. So you can see that I deleted the container, but the volume has a different life cycle. I can specify that the volume may be deleted if I also delete the container. But by default, it's not. Because typically, again, these disks are external to the container. They will survive after a container restart. So I can persist them. Questions?
Bravo. But how about if you have many containers and there are need to use this volume or this storage?
Yeah. Okay, so if I have several volumes, several containers, I will very likely need to have several persistent volume claims. Typically, one persistent volume claim per container. And so Kubernetes will allocate one volume per container. And I will have different volumes. And all of them will survive the execution, the life cycle of the node or the life cycle of the container.
But if you need to read from one database per many containers, you have one storage, one database, and this is need persistence volume read-write many. How about that?
No, you still don't need read-write many because what is a cluster? A Postgres cluster. Postgres cluster typically is going to be one master node and several replicas. They have different disks. Postgres, from that perspective, is not a shared storage system. So in this case, you have one master, two replicas, you'll have 3 volumes. They'll have different data. I mean, they have the same Postgres data, but they are different containers, different storage. And we're going to do that. And we'll see that we'll have different volumes for that.
And what type of file system inside the persistent storage container?
Yeah, okay, that's a very good question because apparently I'm just claiming a volume. It comes from a network volume and it's presented to me as a mounted file system. So where's the trick, right? So as of today, they're supported ext4 and XFS. You can specify them and also some mount options, but it's not perfect. As a Postgres DBA, I would like to see many more options. The problem is that we are not running on VMs. This is one of these situations where we realize this is not a micro VM or anything like that. This is a container. A container is just a process running on the host with abstractions over it, but it's just a process running on a host, right? So what you can have depends on what you have on the host. Because this host could be anything, could be your laptop, as is my case, but could also be a managed Kubernetes cluster on Amazon or a managed Kubernetes cluster on Yandex. They provide the service managed. They will not expose a lot of things to you. So let's say you want to use CFS. I would love to do that. But then they will need to expose this as part of the host and install that as the kernel module and all the things that come with that. So it's limited options. Now, Kubernetes also supports what is called raw block volumes, in which case you would expose to the container a volume device. And then within the container, you can do anything you want with that block device.
And can you say a few words about performance?
Yeah. So there's a lot of abstractions here, right? It looks like performance is not going to be good. Actually, it's very good. It's almost negligible, the difference in performance. Because except for a little bit more limited choice of file systems or mount options, a container is just a process. It's not a VM. A VM has an hypervisor, has indirection mechanisms, needs real emulation of devices. A container is not. A container is a process. And this process runs on the host. Actually, technically speaking, a container is just a process or a process hierarchy wrapped around by a IP space or address space, which is an abstraction provided by the kernel, extremely efficient. Wrapped by a process space, you only see your processes, even though you're running on a larger machine. But that's, again, also provided by the kernel, trivial. And then a file system wrapper that is a bit more heavy because it's typically an overlay file system, but that's for the file system you're not passing. If you're passing a file system like what we're doing here, that it goes directly to the storage. So it's very good for running a database. There's no concerns from that perspective other than the maybe more limited selection of file systems and mount options. Okay, I think it's perfect time for a coffee break. I'm sure you want that. I definitely want that. So let's wrap up for now and let's come back in 15 minutes. All right, so there's much more that we have seen so far. But before that, questions? All is clear? Yeah, go ahead.
Could you please explain, is it possible to do live migration in Kubernetes cluster? I mean, for example, in case of one node is failed, it's online migration to another node without interruption of service.
So live migration, which would be kind of to take one container running on one node and deploy it somehow on another node, is not possible per se. What you can definitely have is a service such that when your container fails, it will be restarted on another node, and all the cluster will reheal and we'll elect a new master, and the new replicas will point to the new master, and the service, we'll talk about the service right now, will be corrected and all that. But it will involve some small downtime, and you need to do the other part. Again, containers are, I know there are some systems for live migration of VMs, but containers are not VMs. Containers are processes that are literally running on the host. And unless you use a system for migrating processes across hosts, which there's only very old technologies that do that and no longer exist, there's not much support for that. But the idea of, in general, Kubernetes and containers is that you need to be prepared for ephemeral workloads. If you're planning workloads that everything is ephemeral, that anything could fail, and if you plan for anything that can fail, you'll build more resilient systems because you're preparing for that.
One more question is, does Kubernetes provide easily tool for upgrade, like from 11 to 12 version?
Okay. So, no, Kubernetes does not provide tools for that. It's up to you. How do you, first of all, how to upgrade, right? Is it a minor upgrade or a major upgrade? If it's a minor upgrade, that's something related to Postgres. You need to deal with that. We need to use the tools that are for Postgres. Now, it makes very easy to some of these processes. If you have, let's say you have a single node cluster. Okay, this is a very simple case, but if you have a single node cluster and you want to upgrade a minor version, the only thing you need to do is change the definition of the container to use a new image, the image that contains the new minor version, and because the data is compatible on disk, just stop the container and delete the container and create a new one. This new one, if you're using external storage, like what we were doing right now, it will attach to the storage, we'll run the new binaries, done. If it's a major version upgrade, then you need to do either a PG upgrade or a PG dump or use logical replication. Then if you're running on a cluster, it's a bit more complicated but there's tools for that. Now I'm gonna show what is a stateful set, for example. Stateful set is a primitive that will help you this process somehow by a mechanism by which, for example, you can say you have one master and two replicas. What you would do is create a third replica. This third replica will be already with a new minor version because it's compatible, it will replicate, and you'll have one replica running with the new version. Then delete one replica. Then repeat the process. Create a new replica, blah, blah, blah. Then, and when you're about to replace the master, you add a new replica with the new version, replicate, and when this replica is done, do a control failover. You'll have a small downtime, but you will have upgraded the whole cluster to minor version with a very small downtime, and all this could be automated with Kubernetes. That's the advantage. But you need to work on this. This doesn't come by default. Okay? Any more question? Okay, so let's move on. So let's recall where we are. I'll take a seat if you don't mind. So this is what we have. This is what we have for now. We have a pod with a name, with the image it's using. We associate also a name, and we mount a volume that comes from a persistent volume claim, and it's mounted here. So far, so good. Let's do now a little bit of polishing. Let's do an exercise in which we're gonna improve how we create a pod on Kubernetes, adding more and more stuff that could relate to production improvements. So the first one is what it's called the namespace. So Kubernetes, we are associating objects with a name. But what if we create tons of objects? They will all be messed up inside a single namespace. Well, similar to the concept of Postgres schemas, there is namespaces in Kubernetes. And within a namespace, we can decide to create the objects in different namespaces, and we can assign different permissions. So we can say this department will only create resources on this namespace, or whatever we want. So we can assign different permissions. So let's start by creating a namespace, because we want to segment the Postgres clusters we're going to create and run them on different namespaces. This is pretty trivial. The first thing that we need to do is create a namespace. And the namespace is pretty simple. It's just the API, the version 1, type, the kind is namespace, and metadata name, this is the only compulsory thing. There's nothing else to do here, so let's just create this directly. Apply as usual, that's F. And this will create a namespace. Here we have PG namespace. Oh, it already existed before. No worries, it doesn't matter. So that's why it gave that warning. Now that we have created a new namespace, we can just repeat the volume. The volume needs to be on the same namespace as the pod. So that's why I need to recreate a volume, or create a new volume in this particular case, associated to the namespace. How do I do that? With the metadata field. So within the metadata field, I specify the namespace I want this object to be created on, and it will be created there. The rest is the same definition I had before. So I'm just adding the new namespace definition here. So let's do that. Actually, it's this one. OK. And finally, same stuff with the pod. The pod, sorry, it will be this one. And the pod definition so far is the same one, except I'm adding the namespace. So in other words, the improvement I'm doing here right now is just creating a new namespace and attaching both the persistent volume claim and the pod, creating them on this new namespace. What do I achieve with this? I segment. Some objects will be in this namespace, some objects will be in that other namespace, and tomorrow I will apply different permissions and restrict access to this namespace for creation or for using these objects. Again, similar to Postgres schemas, just a small tweak, in order to get like a more production ready workload. So let's execute this. We'll create a pod, and that's it. I mean, nothing special. I just wanted to show that there's this capability of creating namespace, and the objects actually will be on this namespace. Actually, if I now say get pods, I will see that there's no pods, because they are, this by default checks on the default namespace, which is kind of the equivalent of Postgres schema, public schema. But if I say go to namespace PG1, then I will see my pod there. So now, for now on, I will use this prefix for any operation. If I want to do an exec, I will do exec on pod PG, and then the command, whatever, and I exit the command. If I don't use the prefix, you will not find the pod. Right? Pretty trivial. Next, there was a question about using the images that come in a personalized way. So depending on which image, we are using here the Postgres official image, right? And Postgres official image, and in general, most container images consume some environment variables. Remember that a container is a process, and process in a Linux operating system, they can access environment, and environment can have environment variables. The same way containers can consume environment variables. And if the image is prepared for that, and this one, Postgres official image, is prepared for that, it can read some environment variables that will affect its behavior. And this is very good to be able to modify the behavior or the options with which this container is running without having to create a new image, which is something, of course, we can do. We can take an existing container and improve it, add stuff on top of it. But maybe it's not needed. So for example, if we go to the official documentation of this official Postgres image, which is on this website, you will see that it's documented here down a little bit here, that there are some environment variables that it supports. For example, we can specify the Postgres password, or we can specify the Postgres user, or the initdb arguments that we want for the cluster or when it is going to be created, right? So we can, this container image accepts these environment variables. So let's go back to our pod definition and add from Kubernetes values to these environment variables so that we'll personalize how we want this container to be created. How is this? Again, pretty simple. So let's go on B. And here I see that I'm adding this. And this basically says, hey, Kubernetes, when you create this image of the container, pass this environment variable to the container. The variable is called Postgres initdb args, and pass this value data checksums. Who uses here data checksums on Postgres? Okay, well, the rest of you who are not raising the hand, do that. Data checksums can save your life, can detect corruption of your data. So you should always be using this option. So for example, this image by default doesn't use data checksums, which I believe is pretty bad. So let's use them. How do I do that? Again, I just pass the Postgres initdb args environment variable, and it will use data checksums. Let's check this. So let's delete the volume, pg1, delete pod pg, and let's create the cluster using this new one. I'll need to create need to delete the volume also, because this Postgres official image, it will only need to be the cluster if there is nothing on the disk. Right now, because we're using a persistent volume, there is data on disk. So let's delete the volume also. I don't remember the name. Okay, this one. So let's say delete BBC. Okay, and let's recreate it. 0, 3. Okay, this will create a new volume, so now we'll have an empty volume. And if we create the pod with this checksums enabled, let's actually get the logs. No, we'll probably not see that on the logs. Let's just do an exec. I need to use the namespace. And if I connect to Postgres and I check if data checksums are enabled, yes, now they're enabled. By default, they're not enabled. So the way this works is because the container image defines an environment variable that it exposes. It could be anything. It's just up to the container image builder. And this is kind of an API also for me as a user. And I read the documentation, which was here, and I say, oh, if I pass the environment variable named Postgres initdb args, then Postgres will pass this to the initdb command. So I decided to, again, pass this value to use the data checksums, and there we go. We've got data checksums. So this is one way of customizing the image without having to build my own image and put it into the container registry, which again is totally possible, but it's simple. If this personalization that comes with the image is good enough for me. Okay, so far so good? All right, let's move on. Now, this is nice, but there is better ways. Let's say that now we need to pass a lot of environment variables. Or let's say that I want to pass the same environment variables to many containers. Okay, I will copy and paste, right? It's okay. I can definitely do that. I'll copy and paste. Good, so far so good. But what if later I want to change those values? All right, I will go to all the files that contain the same environment variables and I will modify them. I can do that. It's just a little bit error prone. Isn't there a better mechanism? If, again, I want to pass many environment variables, or actually any other data, I want to pass, there's many ways also from within Kubernetes in which I could pass information to the containers. Is there any way in which I can represent a given amount of data that I can update live anytime and be referenced by the containers? Yes. And this is called a config map. So a config map is yet another Kubernetes object that I can create that can store arbitrary data, typically key value pairs, but could be like a text file. It's not meant for really large amounts of data, because actually behind the scenes is this persistent in etcd, which is this distributed consensus data store that is not ready for like super big amounts of data. But for config data, key value pairs, config files is pretty good. Environment variables too. And I can define a config map. I can update the config map independently of the life cycle of any container or anything like that, and then reference this from the container. So the next step, we're going to use a config map to put this environment variable and some others, create this config map, and then reference this config map from the container. And you will see later on that I can reference this from multiple containers, but I will just reference a single config map. So let's look into the config map. There we go. It's pretty simple. Again, API version 1, blah, 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 and then kind config map. Again, you see the pattern, right? Kubernetes has objects. That's why I said it's an HTTP object server. Objects have their name, the kind of the object, specify the name. For now on, everything I'll create right now on the PG1 namespace. And then they don't have a spec field, they have a data field. And here I can create any key value pairs that I want. So here I'm going to pass 3 environment variables: the initDB args, the user, and the password. Yes, this is not very secure. Don't copy this into your production files, okay? All right, so let's create this. Pretty simple, pretty simple. I create a config map. Oh, sorry, it already existed. Testing the demo before the talk, but the effect is the same. So, if I check the config maps, of course, I need to check on the correct namespace. Here I can see the config map PG that I just created, and if I would describe it, I can see here the data that I just passed, right? So this is the namespace, and here I have the data. Interesting. So now I have created a config map. This is floating there in the Kubernetes space. The cool thing about the config map is that I can modify anytime. So for example, let's do this live. Let's say I want to edit the config map and add some dummy field right here. Right? So I can just apply, and it updates this config map. And now if I describe this config map, I will see that there's this extra data that I added there. So this is an example of an update operation over the Kubernetes API. Now, if this config map is referenced by many other objects in Kubernetes space, this will get updated whenever a new object is created that references this. So in other words, this config map is also an API I can use to communicate data, configuration data, to other objects in Kubernetes space. Let's see how to do this with this environment variables, which is just one of the few options I can do that. So here I have another file where we modify a pod file such that now it will reference this config map for the environment variables. And it looks like this. Also very simple stuff, right? So I have here this is the name of the environment variables as defined by the documentation of this Postgres official image I'm using. So again, if I go back to the documentation, you see that the variables are defined here. So this is the environment variables supported by the container. And then what I'm doing is, this is the environment variable. And instead of specifying the value directly here, I say, read it from this config map. And then I specify the name of the config map and the key that I want to read. This actually achieves two effects. The first one is that I'm creating this layer of indirection. I can update the config map independently of the objects used in the config map. If 10 objects use the same config map, the same values, I will update it only once. But I'm also creating a level of independence. Postgres image defines these environment variables called Postgres password, Postgres user, Postgres initdb-args. This with uppercase, whatever. This is the standard defined by this particular Postgres image. It happens to be the official image, but it's a given standard. What if I want to refer internally to my other components with a different name? Well, that's exactly what I'm doing in the config map. In the config map, I said only the names are user, password, or initdb-args. I created whatever I wanted. And now I create a mapping. So here, I'm mapping to what this Postgres image requires, what I'm providing from the config map, which has whatever name I want. So it's two layers of indirection from this perspective and creates a lot of flexibility. How does it work? Well, pretty much the same. Let's make sure first there's no container running. Yes, it's running, so let's delete this pod because I'm going to recreate it with this new config map, sorry. Okay, I delete the pod, and I will create it with this now, referencing this config map. This one, and so, yep, config map is created. Interesting is because I'm also passing here the Postgres user from the value we read from the config map, and if we look at the config map, the value is root. There's going to be a small intended side effect, is that now, if you remember previously when I exec into pSQL, I need to suit to the user Postgres, and that's because the cluster is initialized with the user Postgres, whereas when I get a shell from kubectl-exec, I get a shell as root. By using this command, the container that would have been created will be created with root user as a super user also. This is not recommended for production practices, but it works for this demo. So I'll be able to connect with pSQL without having to do to Postgres. Let me show that. But again, because we're using persistent storage, this is only applied at initialization. So actually, I'm going to delete the pod, delete the persistent volume, create an empty persistent volume, and recreate the pod with these options. Let's do that because it's pretty simple. Delete cube. Oh, okay, whatever. Delete pod pg. And the persistent volume claim, the get PVC PG data, PG data. Okay, and now apply, and it's this one, right? Yes. And finally, I recreate the pod. Okay, so if all went well, what is there running? So let's just do an exec. So again, because now the shell is launched as root, and I specified root as the super user for the Postgres being created. Again, don't do this in production. I should be able to run directly pSQL. And indeed, yes, I can run pSQL. So yes, these environment variables worked in other words, and the cluster is created with checksums, and the Postgres superuser is root. Good. Any question here? As you see, what we're doing right now is polishing this container. We're making it better. We're adding a namespace. We're passing environment variables. We're using a config map. Now, is there anything here that you don't like? If I look at this, anything that you don't like here? The password. Yeah. So what we do? Sorry? Encrypt it. Yes, that's a very good option. But it's going to be still a little bit chicken and egg problem. Okay, that's the right word, secret. There's yet another object present in Kubernetes, which is called a secret. Secret, they're not very secret because they're actually not encrypted. You can actually encrypt them, but by default they're not encrypted. They're just base 64 encoded, which for many people they're encrypted, but obviously they're not. But the cool thing about the secret is that you can control the lifecycle of the secret as any other object, which means you can assign permissions. And you can say who can read the secret and who cannot read the secret. There's one advantage. The other advantage of using a secret is that you reference the secret by name and you never actually put the value there. So these config files, because this, if we use GitOps, as I said at the beginning, and you just deploy into your infrastructure automatically by the CI system on your Git repository where you're storing these configuration files, right? You will not have to commit a password. That is a pretty bad practice, right? Don't do that. I did that on this. This is committed on, but this is of course for demo purposes. So let's create a secret. Let's store the password in this secret, and then let's see how we can reference this secret from the container. We're not going to assign permissions to the secret today, but this is something you can do that's left as an exercise. So let's look into that. Secret. How difficult is to create a secret? Pretty simple. Is again another kind of object. I specify the name and the namespace, and then data. And here is a key value pair. It's pretty much like a config map, except that the values I typically specify them as base 64 encoded. This is the same password, just base 64 encoded, so this is not encrypted. Take care with that. It's absolutely not encrypted, right? But the difference here is, again, being this a separate object, I can control who can access this object. And whenever I reference this from, and typically this kind of secret you will not commit to the Git repository anyway, because again, it's not encrypted. Maybe you'll create a secret in a different manner. There's many different to create a secret with an API call, for example. You will not commit this to the config file, to the Git repository ever. And now, from now on, all containers will reference this as a secret. Otherwise, it looks like a config map, right? Well, it's pretty much like a config map. So how do we reference this from the pod? Pretty much the same. So let's create this from before. Let's create a secret. Yeah, already exists. Sorry about that, but nothing changes. And let's see how to reference this from the config map. Sorry, from the container. Well, this is just the only difference, right? That instead of saying config map key ref, I say secret key ref. And then I specify the name of the secret. In this case, it's called like this, and the key. And that's pretty much it. So the cool thing in this case is that I'm not referencing this as a particular config map or direct value, but rather I'm referencing a secret which can have a different life cycle and different security considerations as what could be a normal config map, for example. And so let's recreate the pod just to make sure that this works. By the way, you see that what I'm doing all the time? Just let's backtrack just a little bit. So just by specifying a small YAML file, I'm pulling a container image from the official repository, which contains Postgres already prepared. And by just running a few YAML files, I'm all the time dumping, creating, restarting Postgres servers like this. Isn't that cool? I think it is. Normally, if you would do this, by hand installing, it will take hours to do this. Now we're very, very efficient here, and we'll get even more. So, okay, let's apply also this one, the pod, and the Yeah, that will not work. Pods. Okay, pod is there, all is running, so far so good. Let's look a little bit more how we can further improve this pod definition, which is already getting a little bit interesting, a little bit more advanced. What else can we do? I don't remember, but let's check what else we can do. Oh, labels, pretty simple. So another thing, and this is pretty pervasive in Kubernetes, and I strongly recommend you to do this. Attach labels to the objects. Any object in Kubernetes supports to be attached an arbitrary amount of labels. What is a label? A label is a key-value pair. Could be anything. You can define the key, you can define the value. What is this useful for? It's useful to tag the objects. If you can attach properties to these objects, their metadata, you can then classify them by this. You can query them by these properties. And they are also used internal by Kubernetes. We'll see a bit later how to use this by classifying this. And they can allow you, for example, to say, what is the team that owns these objects? So, for example, I create some volumes, I create some cluster, I create Postgres clusters. I can say, oh, this team is the owner for this cluster and these volumes. So if that fails, we can know whom to ask for. Some people even use that to write on these tags the on-call support number. So if some object fails, you check the metadata and ring the phone and call your support service. Or you can associate different cost centers. So if in your company you have different cost centers, you know which objects are causing which cost. So all this you can just attach to arbitrary metadata, and I strongly recommend you to do this all the time. How to do that? Extremely simple. We just go to this new definition of the pod, and here we say that we added on the metadata section some labels. In this particular example, I'm just attaching one, which is environment production. Oh, this pod, because we're still a pod, this is going to belong to the environment production. So I can classify things by environment. Then I can query and say, give me all the objects belonging to this given environment. Or I can say, what is the responsible team? And I can know who to blame. Or who to, of course, greet if everything works very well. Or which is the company providing support for this kind of object. Whatever. Literally, I can do anything. Actually, in this case, because this is just an addition to the pod, let's just apply this directly. Cool. So I have added this information, and actually, for example, if I do describe the pod PG, I will see that now the labels are attached here. Okay? Pretty simple. And last but not least, in this effort of polishing this port definition, right? Let's look at another area which is interesting, which is to add probes. Probes are health check mechanisms that are automatically provided by Kubernetes. So in this case, we're going to add what is called readiness probe, which is a check that Kubernetes will execute on our container on behalf of us and make sure that the container is providing its service. So in this case, we are launching Postgres. And Postgres, we know that runs on a TCP port 5432. So we're going to ask Kubernetes to check if this service is available. And if it's not available, it will not say that the container is created. This is very useful because if it takes some time to start the container, we can make Kubernetes wait until this readiness probe passes to tell the rest of the containers or that depend on this one that the container is ready. How to do this is also very simple. Let's go for this. And the only thing I need to ask here, add here, is this readiness probe. And this means that the container is ready for being used, and it's very simple. In this case, typically this supports TCP probes, but also HTTP, which is the typical case. For us, we can do HTTP because Postgres doesn't do HTTP, but we have TCP. Of course, this is not testing whether the connection succeeds, it's not running a query against Postgres, just checking that the TCP port is open and accepting connections. But other than that, I can specify some further parameters like the initial delay and how many time between tries. But with this, I will make sure that when the container if someone depends on this container, It will be only got started, when this container is marked as ready, which means Postgres is running effectively. Other than readiness probes, I can also set up startup probes, which apply when the container is starting, and liveness probes. And liveness probes are probes that execute all the time, continuously, checking the health check of your container. And if it fails, Kubernetes will restart your cluster container automatically for you until it passes again. Let's add this quickly, and I'll move on to the next one. Any questions so far? Okay. All good so far. Let's, yep, Postgres running there. What else? So far, we've been able to create pods. A pod, we have improved significantly this pod definition. We've used environment variables, we have used labels, namespaces, config maps, secrets. You see, we have already created a bunch of objects in Kubernetes. Now, let's try to move to the cluster. What if we need to create more than one pod? What if we want to create one master and two replicas? Well, if we were talking about something stateless, like an HTTP server, this would be absolutely trivial, very simple to do. Because we're dealing here with state and with databases, this is not as easy. And actually, we're going to create a fake cluster right now, a cluster where all the nodes are going to be masters, which is obviously not what we want. But it will not have enough time to do it. It's doable, obviously, but we will not have time today to do that. So I'm going to show some basic building blocks with which you could create Postgres full-feature Postgres clusters. So the first one we're going to look at is what's called a replica set. And a replica set is basically a set of pods created equal, where Kubernetes will take care of keeping the cardinality as desired. So let's say I want to have 3 replicas. They're called replicas on a replica set. And if one container dies, it will spin up a new one so that I have that same number of replicas. Other than that, because the containers are the same, I provide them as a specification of what type of container I want to provide. It's called a container template. So how this looks like. And just last bit. So I said replica sets. Replica sets allow you, again, to control the cardinality of instances. But there's still a better object that builds on top of replica sets, which is called a deployment. So you can create directly replica sets, that's fine. But deployment builds on top of replica set, and that's capabilities for managing the upgrade lifecycle. So sometimes you will say, oh, I want to upgrade the containers versions. And this, again, is super simple for stateless, is harder for stateful. So I'll not get into this topic. But you can definitely do that. And because of this, because anyway, deployments take into account some mechanisms for rolling upgrades, that it's called, they're always preferable. So let's make a deployment which internally uses a replica set to create more than one Postgres container. So how does it look like? API version deployment belongs to a different namespace on Kubernetes API, so I just change the version. And then the object deployment. This is the same as we had before, name, namespace, and then the labels, and the spec. The spec here changes from what it was previously the pod. Here first I need to say how many replicas do I want. Let's actually make this 2 because otherwise it's going to be, no, actually I'm going to make it 1 and later change to 2, so you'll see how this works. So number of replicas I want. Let's start with 1. And then I'll specify a selector. What is a selector? Something that looks for labels. You'll see now that also Kubernetes uses labels internally. And I'll say, I want to belong to this deployment those pods that have this label, key app and value PG1. We'll see why we do this. And then we specify the template of the pod I want to create. And inside of this template, what is inside looks pretty much the same as we had before as a pod. We have the metadata with the labels, and we have the spec. And the spec is pretty much the same what we had before. The containers, the list of containers, so far so on, we're using one container with our name, the image, the readiness probe, the environment variables, and the volumes. Okay, so pretty much the same, except that we are wrapping this inside of a template object, and we add the replicas and the selector. So if you notice, we're also adding here one extra label, which is the same that we are putting here. What does it mean? The reason for this, and this is compulsory, you always need to put these match labels here the same as the labels you are exposing on the pods. These are the labels that will be copied to the pods that are created according to this template. Now, the deployment groups object by a criteria. So which containers belong to this same deployment? And that is by filtering by label. So in order for these containers that will be created within this replica deployment to belong to the deployment, I need to specify that they have this label and that the selector that makes which containers, pods, sorry, belong to this deployment will need to have these labels. In other words, they need to match. So this is the object, and let's actually create it. Should be pretty straightforward. Let's delete the other pod just to free some resources. Pod PG was called, right? Yes. Okay. And let's create this deployment. Sorry. Okay. So now, if we say get deployments, we should see that there's a deployment there. We can definitely describe this deployment, dep PG, and it will provide us some information. The same we're doing this describe with any object in Kubernetes. And okay, here you see replicas, interesting information. One desired, one updated, one total, one available, which apparently means that, yes, has created some pod there. We'll check this right now. And we also see that this deployment supports some concept relating to rolling updates and rolling strategy. Again, this is to upgrade the versions of, provide some mechanisms to facilitate the upgrades of versions within the containers, which again are very convenient for statelet workloads, a bit more difficult for stateful, but it's still interesting. Cool. And so let's look at the pods. Get pods. Now, this is the name of the pod. Because it is a deployment and I create pods on demand, I don't know exactly what the name of the container would be. So the deployment adds a random string to the name of the pod. But that's fine. So yeah, I have the pod running, and if I do the exec as I was doing before, I just need to replace, of course, the name of the container. All should work fine. Correct. Now, this is a replica set. And the cool thing about, sorry, deployment, which is, yes, uses a replica set underneath. The cool thing is that I can control the number of replicas, right? Kubernetes does this for me. So let's actually fire more replicas. Let's edit this file. It should be here. And instead of one replica, actually, let's say 3, because I want. So I just edit this file. I apply it. And again, the same will happen. Kubernetes will realize that the object identified by this URL, internally there's a URL for this object, will have an update. And this update will mean that the deployment has been upgraded with replicas 3, which will in turn trigger an action on Kubernetes to create more containers. So is this true? If we go to the deployment and do describe the container, we see that, oh, yes, there's 3 replicas right now. Interesting. So let's get the pods. Yep, there's 3 pods, and they're all running. And we can see that the first one was started 2 minutes and 30 seconds ago, the other one 32 seconds ago, which is approximately when I changed this value from 1 to 3. So this is pretty cool because with just a few more lines of YAML, now I can control the number of instances of a cluster with editing one value. Pretty cool. Now, there's a small problem here. Anyone can tell me what the problem is here? Okay, that's a good question. How do I get it? Can anyone tell me the command? Can anyone tell me what command to type?
Get volumes.
Okay. This one, by the way, let me delete this because this shouldn't be here. So there's only one. So what does it mean? Are they sharing it? Yep. So this was the previous question, right? What happens if they share the same storage? It's pretty bad. Basically, I'm corrupting data pretty badly. I have 3 master instances all using the same storage. No, don't do this. Actually, if I get the pods, we'll see that this is the case, because if I get the logs from the first one, we'll see that Postgres very likely started correctly. But if I get the logs from any other of the containers, the pods in this case, we'll see that very likely, yep, they're not happy. Yep, they say, this is kind of corrupted. Let's recover this. So, yeah, not good, not good. Yep.
How to protect PVC for not interrupting that? How to protect storage?
And how to protect, sorry?
How to protect storage for that? How to protect storage?
Okay, okay. So the good thing about Kubernetes is that, as you can see, everything are objects, right? Of different kinds, but everything are objects. And Kubernetes comes with a mechanism called RBAC, Role-Based Access Control, which allows you to control access to objects. So you can say who has access to which objects. Now, for this particular case, we're not going to be using RBAC. We're just going to make directly use of another object, which is better than deployments. Deployments are not meant for stateful workloads. So don't use deployments for Postgres. I just wanted to teach you about deployments. But deployments are not good for Postgres. There is a better object for managing stateful workloads that is similar conceptually to this deployment, which has this concept of replicas and templates, and this concept of rolling upgrades and strategies for version upgrade, but has also the concept of a stateful for each pod. Anyone can tell me which object is this? Stateful set. So let's do the same, but with stateful set. By the way, if I delete this deployment, the pods will also get deleted. You see that they're terminating. Let's watch on this, and we'll see that they eventually disappear. Okay, so there we go. Let's see how to do this with a stateful set. Stateful set also relies on a service. So let's see another kind of object on Kubernetes, which is a service. What is a service? A service is an abstraction also, this time on the network side. So let's talk a little bit about the network. Kubernetes pods, they have their own IP space, IP and port space. And they are created with an IP that we don't know. We can actually check the pods. Each of one will have its own IP address. And each time a pod dies or gets rescheduled or gets created, a new IP will be created. They're dynamically, typically. So we don't know where the service, where the pods are. So where's my Postgres? So the cool thing is that you can create a service. And a service is something that will have its own IP. And then you can say, this service matches with this container or containers. And Kubernetes will do all the magic for you, such that if you connect to the IP of the service, you will get to the container or containers that are behind the service. If there's more than one container, it will be load balanced. If there is one, you'll get connection. It does this by a combination of proxying or typically IP tables. It's very complex network magic. It's very cool, but it works beautifully well. So let's look how to create a service first. Very simple. Kind service, metadata same as ever, as usual, and then the spec. For the spec, I specify the array of ports that I want to expose as part of this service. Here, I want to specify port, Postgres port, and I'm going to use a selector, the same as we were using as part of the deployment label as a selector. Here I use a selector, which means every pod that has this annotation, this label, will be connected to this service, will become an endpoint for this service. And now, let's create this. Create a service. And now let's look at the stateful set. So the stateful set is very similar, except that it's a different kind to the deployment. Very similar. But I need to reference a service. So this service that I just created, I will reference from the replica set. And apart from that, everything remains the same. And I will create a stateful set. So let's create this. And I'll get a stateful set. Right, so there I go. It is creating. And if I get this, if I see the pods, I see that there is one pod being created right now. It's running already. In this case, with the stateful set, the pods are named with ordinal numbers. So the first one is going to be 0, the next one is going to be 1, and so forth. So actually, if I edit the stateful set and add more replicas, let's do that. Okay, and if I get the pods, I see that they are creating. Cool things about stateful set. Stateful sets will create one persistent volume claim if I specify a persistent volume claim template, which, by the way, I did. Let me show that. You see that here, instead of specifying a persistent volume claim, I am using a persistent volume claim template, which means the stateful set will create for me under the hood one persistent volume claim per pod. So this will result in the creation, in this case, of 3 persistent volume claims, which will, of course, provoke the creation of 3 volumes, and each of one will be attached to each of my containers. So now I have achieved what I wanted, which is I have 3 Postgres containers, each of which has its own volume. Now we're not corrupting anything. We just have 3 masters. It's still not what we want exactly, but at least we are not corrupting data. We have different volumes. And you see the YAML file is pretty much the same. Nothing significantly changes. Now, if we look at the pods, we see that we have the three pods here. And if we check the PVCs, we see that, yes, it has created 3 volumes right now. So stateful sets are typically the building block with which you would build a Postgres cluster. Of course, we're not done here. What would be left to do to create a truly Postgres cluster with 1 master and several secondaries? Well, we need some support, in this case, not coming from Kubernetes. We need something that will make a leader election. We'll say, oh, because the pods are equal, right? They're the same. They come from the same template, the same image, same values. So we need a software that will say, hey, you're going to be the master, you're going to be a replica, and because you're going to be a replica, start replicating from this other node. And there's software for doing that, and some of them is, for example, Patroni. And Patroni is a Postgres software that will run this job. So in this case, we'll need to change the image and use an image which is just Patroni and pass some extra configuration for Patroni to work. This is not going to happen. I mean, this is not part of this exercise today. And I want to show you a few other bits. But if you're interested on how to really build a fully functional Postgres cluster, with stateful sets, many of the things that we have explained today, and many others that we haven't explained yet today, and have a Postgres cluster which comes directly with high availability, with a leader election, with monitoring included, with automatic backups, with exporting metrics to Prometheus, with connection pooling, with HTTP proxying for metrics, and many other things with graphical user interface from the web interface, all that. I will be presenting another talk on Wednesday, I think at 12, but I'm not totally sure, about an open source software that we have built called StackGres, which is exactly what I'm describing, is Postgres with all these things on Kubernetes, all done in a very, very simple manner. Just edit a few YAML files and you'll have a Postgres cluster created with again, all these pieces that I mentioned, connection pooling, stateful sets with its proper volumes, with monitoring, and many other things. Automatic failover, automatic backups, all that created for you. So, join me on Wednesday, I think at 12, but I may be wrong, if you want to know more about that. And before wrapping up, I have a few more quickly things. So we have already stateful set, not totally correct from the Postgres perspective, but correct from the Kubernetes perspective. What else can we do here? So I don't think I have it here. No. Oh, I'm sorry. I thought I had another example here. The last concept I wanted to discuss is about a pattern which is called the sidecar pattern. And basically what it is that if I have, remember that I said at the beginning, a pod can contain one or more containers. It's actually very usual to have more than one container within the same pod. And there's one option within this capabilities, which is share namespace. So if you recall what I said at the beginning, I said that a container is a wrapper over some process or process hierarchy, and that wraps the process space, the network space, and the file system space. But what if I want two containers or more to collaborate as part of the same space? What if one wants to speak to the other one, for example, via Unix domain sockets? Or TCP IP, but within the same network space, so that they are exposed as a single unit to the outside. Or if I want one service to talk only on local host and the other service to be exposed as a service to the external elements, right? So this is what you can achieve with a pattern called sidecar. And this sidecar is, I will create more containers within the same pod that share the same namespace, and so they can cooperate between them. This is something I will also show extensively on Wednesday in my talk. What I'm missing here, and this is the last bit, and I'll take a few more questions if there's any, is that what does this service mean? So we created the service. Yeah. Okay. May I finish just this bit, and I'll take a couple more questions?
If I correctly understand, you need a DNS provider for that.
Okay, that's a very good one. Thank you. So yes, because I created the service, let's look at that. If you remember, I created this service first, right? The service PG, and this is a mapping. And this service, if I get it, service PG, right here I have the service, and here's the selector, and here's the IP of the service. Now, the service by itself, as it is right now, it is just an IP created by a mechanism called cluster IP. I don't need for now any specific DNS service. Now, it is true that Kubernetes also comes with one service called core DNS, which you can leverage. If it's available in the cluster, in this cluster is available, I explicitly enabled it, it will also expose this service as a DNS name. And this is very cool. Let's just see briefly how this works. So, right now, I have some pods running here, right? Yep. So I have these pods running here. Let's try to connect to the master pod. Typically, I've always, throughout this demo, I've been using all the time the connection via kubectl exec, which runs a command inside of the container. That's actually a bit tricky. I mean, it works, but it's not how you're supposed to use Postgres. You're typically going to use Postgres by creating a separate container, which will be your web application or whatever is using the database, and connecting via IP to Postgres, right? So it was a bit of a trickery what I was doing here. So let's launch another container, which will be the client, and make it connect to the nodes in such a way like any other application. So we can do this with a shorthand called kubectl run, and let's say this is going to be client, the image, don't forget the path. Let me just copy this, it's going to be faster. So with this command, I will just deploy to Kubernetes, just another image. Hold on, this is super interesting, but not exactly what I wanted. Okay. So now, here I have a client. And this client, I use the same Postgres image just because it comes with pSQL. So I can check connectivity with pSQL from this container to the other containers. So let's say I want to connect to the master. And let's say describe pod. This pod. So let's get the IP of this container. It's this one. And if now I get the pods and I exec, okay. Sorry about this. Okay, so this is a client. If I do a pSQL and I connect to the container port and I type that super secure password, I can connect. So right now, I'm not using the service. But what I'm doing is I created another container external to my Postgres cluster. And instead of using exec, well, I'm using exec, but to connect to the client. But if this client would be running an application by using this IP, it could connect perfectly to my container. The problem is that if the master node dies, this IP is going to change. So if I delete the pod, the master pod, if I delete the master pod, which of course will be recreated because I'm running a stateful set, which is very cool. It will bring up a new one automatically. But it will come with a different IP. Yeah, it's creating, as you can see there, it's already running. And if I go to describe, we can see that the IP, I don't remember the other one, but should have changed. Now, what I can do instead is reference the service. So if I get the service has its own IP, and this IP is going to be stable because this IP, as you can see, is connected to all the endpoints that match the labels that I wanted to. So, and if the pods change under the hood, the endpoints that the service reference to will be updated, but the service IP will not change. So my application, my client, should connect always to the cluster IP and then should have a stable address for connecting to the cluster. If I connect to the client and I say this, I connect to the cluster. Actually, it's a bit weird right now because I have 3 instances in this cluster. They're all master again, and I don't know exactly which one I have connected right now. But what I wanted to prove here, because right now they're load balanced, but what I wanted to prove is that this works, right? And so if you really would have one master and several secondaries, you would expose different labels. Maybe you're very likely create different services, one service for the read-write connections, one service for the read-only connections, with different names, with consequently different IPs, and your application would choose. And that's pretty much it, barring some new questions, what I wanted to explain today. And before these last questions, I invite you to come on this talk on Wednesday to explore much more detail, handmade, I mean, not a handmade solution, but a solution already prepared for you so that you don't need to do all these YAML things that we are doing here, which is pretty good, probably. And I hope you get something home back, but it can be complicated to end up maybe creating around 50,000, 60,000 lines of YAML code to create this when you want a real Postgres production cluster with monitoring and backups and all those things. And that is a bit tedious. But there's a software that does all this for you, which is called StackGres, again, open source. I'll be explaining that on Wednesday. So before that, hope to see you there. Questions? I think you had one or no?
How you find which pod is master for this IP? If I connect, if client connect to this IP, to which pod will connect?
Yeah. So remember the service definition, right? the way a service is exposed is this is the ports that are exposed by the service, and this is a selector. And selector can be anything. So what I do when I want to connect only to the master is that I would say something here like, let's say, instead of saying app PG1, I would say role master, for example, right? And then, if I have a service like Patroni, that depending on who is the master, will change the labels dynamically on the pod, then this service will only point to one node. You see how important labels are in Kubernetes. Objects also, controllers, the software that is running can change, manipulate these labels. So for example, Patroni, this high availability software for Postgres, can change dynamically the labels of the pods it is running. And it will do that. And it will expose a label like this. On the master nodes, it will be master. On the other ones will be replicas. And you can create two services, for example. One for the master, that will be only have one instance only, and one for the replicas, which will be load balanced.
So selector is kind of a label. Yeah?
Yes, selector actually could be a much more complex expression. You could say and or operations in operations over labels. But yes, typically something like this. For example, it could be like app PG1 and role master, for example.
Makes sense.
I think there's another one over there.
In case of net splits, is it possible that Kubernetes will schedule two pods with the same role on two different nodes, and that will corrupt the data?
Well, it depends on, in this case, so we are relying on stateful sets, right? And stateful sets go as far as they go. They don't understand Postgres specifics. Even though they're stateful sets and they assume that each node has its own storage, they don't have the notion of replicas and master nodes. They assume all are equal. So this is very good for distributed databases that they don't care who's the master or they have internal mechanisms. Postgres is not like this. So you need some extra help from some extra software. In this case, Patroni. If you rely on Patroni, Patroni warranties that it will not apply the role master, the master role to more than one node. Could be 0 or 1. 0 temporarily and 1, no more than 1. How it does warranties that? It's not a matter of this, but it uses a consensus distributed database, which in the case of Kubernetes could be Kubernetes API, which ensures that there could be only one leader by using some logs and so that.
So we need help from Patroni to
Yes.
actually keep systems safe. Okay,
Yes.
Thank you.
I think there is space for some. The cool thing about Kubernetes also is that you can create your own objects. And this is the subject of what I will explain on Wednesday. And they can have the spec you want. You can have the fields that you want. And this can be very high level. You can say number of Postgres replicas, for example. And there is place for a controller. The controller is the software that monitors these custom resources, these custom objects. There is a space for creating one that will support this, will use a stateful set and support this notion of master and replicas. But no such thing exists. So you need to build on top of this by yourself. Okay, anyway, I think we're a little bit over time and I don't want to have anyone come late to lunch. What I can do is, I believe we can wrap up, but I'm not in a rush. So all these extra questions, just come to me. I'll be happy to answer them. Yep. Thank you. Thank you very much for attending.